Today we are doing 5.4 equilateral and isosceles triangles. I forgot to grab, so I did buy pens. I did in fact buy pens. They were downstairs in my backpack. I'm too lazy to go back downstairs to go get them, so I'm not. So once again, we're gonna using the nice pens. Isosceles triangles. We're gonna talk about them first. Put an S there, it'll make it look nice. So we did talk about triangles at the beginning at 5.1, but not like that in depth. We just kind of just showed like, hey, these are the triangles that we work with. Ha ha ha. No, well, we're actually gonna talk about like some properties that these triangles have. First, isosceles, then equilateral after. But we're going to talk about the properties. Now, remembering like what we did already when we sketched out an isosceles, we had tick marks right here. And remembering what these tick marks are, these mean congruency, like congruent sides. So congruent sides. Cool. Now, there's actually like anatomy to an isosceles triangle too. In the fact that these congruent sides, they are called the legs of an isosceles triangle. So that's good to know. Cool. And with all the anatomy with a triangle, we will label everything else out too. Like this right here, the bottom line, this is called the base of the isosceles. Makes sense because we have the legs right here. The legs are congruent to each other. They go onto a base. Makes sense. Cool. And then we have angles down here. These two in specific. We'd call them the base angles. All right. Nothing too wild. Base angles. Cool. And then we have, the angle up here, the one that makes everything 180 degrees using the triangle sum theorem that we learned in 5.1. This is called the vertex angle. Cool. So there's some theorems and some wordplay. There's some mathy stuff that goes along with doing isosceles triangles. And we're going to go with them today. We're going to learn them. In our case, we're going to be doing Theorem 5.6, the base angles theorem. What this theorem states, I'll write it in pencil, I guess. I'm so bad. I'm too lazy to go downstairs. I don't have time to actually watch through everything today. I got to watch the Lions tonight. If two sides of a triangle are congruent, comma, then the angles opposite them are congruent. What does this statement mean? So take in consideration this up here. We'll actually draw out an isosceles triangle. And I'll put it down here. What this theorem is stating, and like what we have already is the tick marks right here on the sides. So these two are the same. So if we have congruent marks, then we are saying that these two angles down here, the base angles, are congruent with each other. So I would mention if you have tick marks, the congruent marks. Use real language. Congruent marks. Then the base angles are congruent. Cool. That's what this theorem is stating. So like if that would mean like if this, yeah, you guys played around with this when we did the triangle thing. You guys played around with it. So that's what, and you've kind of noticed, or at least like when I played around with it, you're able to see that both of the angles were pretty close to each other. Might have like a decimal point or two off, but they were pretty darn close to each other. This is the theorem why it happens. So cool to know. And so here's a cool thing. Remember what a converse is? We're going to be using converses. I guess converse. Take a P and Q from a regular statement. It would end up being a Q to P. Switching our if and then around. We're going to be having converse statements throughout this lesson. Speaking of, we're going to have a converse of this theorem right here. So that means we're going to be switching our Q and P around, or switching our P and Q around. So take instance, this is our P, this is our Q. I forgot about the congruency. The congruent, this is part of the Q2, but we're flipping our P and Q around for our converse for this statement. So I'm going to write converse of theorem 5.6 because that is a lot less writing than what's in my notes. And it states that if two angles of a triangle are congruent, then the sides opposite to them are congruent. And I'm going to draw a picture that goes along with this as well. So take just ordinary triangle that we have here. If these two angles are congruent, I'm going to have my blue be my adding. Boom. Congruent marks. They are the same now. So a better writing is that if base angles are congruent, then the legs are congruent. Cool. That's isosceles triangles, and that's the two theorems that we can work with when we are starting to solve isosceles triangles as well. So we're going to do an example of that. And it will be our example 1. And in the figure that I will draw, angle A is congruent to angle B, and we need to name the two congruent sides. So in our case, let's just say this is B, A, and C, and angle A and angle B are congruent. So by our theorem, by our converse, the converse of 5.6, that means that these two sides would be congruent to each other, and that would mean AC is congruent to BC. All right. Example 2. I have another example on this. So I'm going to draw my figure out. And, okay, it'll be like that. Say that's going to be my figure. Let's say we have points H, G, K, and J. I'm going to say that, I guess I'm not going to write anything else. We're going to have that figure. Let's say for problem 1, we're going to have if HG is congruent to HK with segment, then blank And then we'll have example 2, which will be if angle KHJ is congruent to angle KJH, then blank. All right. So looking at our figure and just looking at what we're about to work with, we have HG and HK. Those two are congruent. So I'm going to find HG, which is this segment, and HK, which is this segment. So if these two are congruent to each other, then that means we should have that angle G and angle HKG should be congruent to each other, because those are right at they're the base of this isosceles triangle. These are the legs of the isosceles triangle, and this would be the vertical angle. So that means that angle G is going to be congruent to angle HK G. Remember that K is going to be like the actual, like the middle part. So like HKG or GKH. It has to be 3 letters. If you just say angle K, you could either mean this angle right here or this one right here. And we don't want to look at this one right now. So make sure you have your 3 letters for that. All right, next one. I'm going to use blue. Actually, I have orange. I guess that might blend in a little bit, but oh well. So I have that angle KHJ, so KHJ, this one, is congruent to angle KJH, so congruent to this. Then that would mean my 2 legs would be congruent. So this is my base right here. This is the base. So that means my legs, this one and this one, are congruent to each other. So that means segment KJ, I guess we're writing in colored pencil, is congruent to segment HK. Cool. So just identifying what's what and knowing your anatomy of the isosceles, knowing what's a leg, what's a base. The base angles go with the base. The legs are right above it, and then the vertex angle. I guess we're not working too much with the vertex angle, but knowing your being able to identify what is the isosceles is good. Okay, dokie. We're on to equilateral triangles. Equilateral. Oh my gosh. Triangles. So, drawing out an equilateral. Equilateral and equiangular. I'm going to write that on top, actually. Equiangular. They both give a lot of the same information. And the fact that in an equilateral, all the sides of that triangle is going to be congruent to each other. And that means all of the angles inside as well are going to be congruent with each other. It plays into each other. Yes. And we have a couple theorems that go with this. That combines both equiangular and equilateral together, which, remember the terms that we have used, the corollary, and we're going to be using those. I forgot to mention, was it this? Yes, it was. This converse of Theorem 5.6, this is actually Theorem 5.7. It actually has like its own name, but it's the converse to this one. So, but it has a real name. I say that because we're using corollaries right now, and that they are based off of those 2 theorems. And I forgot to mention that. So corollary 5.2, and it goes for based off of Theorem 5.6. It states that if a triangle is equilateral, then it is equiangular, and then we have another corollary that goes with it, and it's Corollary 5.3, and it's based off of Theorem 5.7. And it states, it states that if a triangle is equiangular, then it is equilateral. Which is why we can combine both of them together to make one triangle. Yay! We have some examples to work with this. In the case of that, we'll do example 3. Example 3. I'm going to draw my triangle. These are equilateral problems, by the way. The ones that we are doing. Boop, boop, boop. And let's say I have this one being 2x. And my goal is to find the value of x. That is my goal for example 3. Find the value of x. So, considering that I have an equilateral triangle right here, all the sides are the same, I'm going to use my Corollary 5.2 to state that if this triangle is equilateral, then it's also equiangular. So noticing that I have 2x right here, I'm out of focus, Jesus. I'm out of focus. I have 2x. So I can put in 2x up top, right here, 2x. And then 2x on the right side, 2x. And remembering the triangle sum theorem, adding up the 3 angles inside equal 180. So that means I can do 2x plus 2x plus 2x equals 180. I can combine everything together to get 6x equals 180 over, now I can, 6x equals 180, divide by 6, giving me a x equals 30. Coolio. All right, last example that we are doing, example 4. This one's going to be a lot more complicated. And we're going to be, I guess I'll draw the figure first. Because I think this is going to be the hardest part for me. It's just drawing it. Oh boy. That is not equilateral. Oh God. Oh no. You gotta trust the markings that I put on this figure today. Our goal is going to be to find the values of x and y. I still need to write in everything that I need for this, which will be coming up, which is 28 here, a 28 here, a 4y here, and a 2x. I also have congruent markings on the inside of this triangle. So this is what I'm given. I need to find x and y. So here is my deal. The best thing that I should do now is just to mark out everything that I know. I'm going to use blue and I guess orange and maybe my pencil to help me with this. So I have congruent markings inside of this triangle right here, and there are for each angle that's inside that triangle. So remembering Corollary 5.3, if my triangle is equiangular, that means it's equilateral. So that means that if these are all the same, then my sides are all the same. So I'm going to start putting tick marks on my sides. Put a pause in that for a second. I'm not working with it. Also, I know that this is 28 right here. This equals 28. This is also 28. I know that my drawing does not show it nicely, but they have the same value. So I'm going to put put a marking right here. So a couple things that we can note, like off the cuff now. This, finding y is going to be easy. And then I guess we'll wait for this. We'll find y first. We're going to find y before I start talking more. All right. So I said put a pin in this, the 28 for y. We're going to find y now. So I'm going to put 28 equals 4y together. They are the same values, so I should be able to put them equal to each other. And then it's just moving forward to the other side to get y equals 7. Cool. So we got y, we need to find x. So noticing that I have 2 tick marks right here that look a little leggy to me. They look like the leg of the isosceles triangle. Remember the anatomy that we have of the isosceles. If we have 2 legs right here, we can use our theorem stating that if 2 of the sides are congruent to each other, then the base angles are going to be congruent to each other. So that means I can put 2x on the other side. All right, so we're kind of at a sticking point where we don't really have a good direction to go to, because we can't set this equal to 180 at all because we don't know what this value is. But there is a way that we can find it, and that's using one of the techniques for finding angle measures that we have in our arsenal. In our case, I know that this is 60 degrees. Because it's equal angular, it is 60 degrees. And wouldn't you know, this is a straight angle. I didn't draw it straight, but in your figure, it should be a straight angle. If we continue this over to the other side like so, it forms a linear pair. So, linear pair. I'm going to write it out. Linear pair. Oh my goodness. What we can do with a linear pair is that we can subtract 60 from 180 to get 120. Remember, linear pairs add up to 180 degrees. And that means I can put up my angle right here being 120. Because this forms a linear pair, which gives me 180 degrees. That's a straight angle, which is a straight line. Cool. We're in good motion right now. Now, I can set this isosceles triangle right here equal to 180 to get my x value, because I found 120 from being a linear pair of 60. So cool. I'm going to set equal 2x plus 2x plus 120 equals 180. And then I'm going to just combine everything I know. For x plus 120 equals 180 minusing 120 gives me 4x equals 60. And then dividing 4x, well, dividing 4, not 4x, would give me an x equals 15. And that is my solve. I solved it. I got my both x and y. If it helps you, I would draw this in like a different, you could draw it like differently. Differently as in you could flip it. Flip this triangle to make it look nicer to help you, like doing 2x, 120, and putting the sides here to make it help you, and you can piece it can help you to better visualize it being an isosceles. Or you could just move the triangle that we have already outside, just so we're not having like all this equal angular triangle right here being very annoying. I don't like it there. It's taking up space. So if you need to move stuff around, draw different figures, do it. It'll help you. But that is all for this lesson. You should have homework for this. And I'm going to go watch the Lions.